What you're about to see is an amazing transformation and healing of the land. Healing of the land accomplished by coal mining through a technique called remining. Ohio's coal operators are conducting secondary remining operations that recover additional coal reserves and provide no-cost reclamation and remediation of past mining practices. These remining efforts are restoring streams, wetlands, and aquatic resources within previously impacted watersheds. In the next several minutes, you will learn about an exciting technique used to reclaim mined land, the challenges of remining, and the incentives to encourage the process. Early coal mines were relatively small, but as the years passed, they grew in areal extent. Until just before World War I, virtually all of Ohio's coal was produced from underground mines. The appearance of the steam-powered coal shovel around 1914 permitted coal surface mining to develop, and by World War II, surface mining had become very important statewide in terms of total production. During that time, the standards laid out by the law were inadequate, and as a consequence, many surface coal mines left behind a scarred landscape of abandoned mine lands. Such abandoned mine lands contain exposed, dangerous, unstable final cut high walls and steep piles of unreclaimed excavated material, called spoil, creating fall hazards for humans and the potential for rock falls. They also often contain streams and water impounding mining pits contaminated with iron, manganese, aluminum, other metals, acidity, dissolved solids, and sediment, abandoned underground mine openings and auger voids, eroding unreclaimed spoil, and the remnants of coal cleaning facilities and areas where vegetation cannot thrive. Water accumulating in abandoned mining pits can be polluted by acid mine drainage, created by exposed spoil and high walls. Pyrite, or fool's gold, is a mineral containing iron and sulfur. It is common in the rocks in the coal-bearing region of Ohio. When exposed and unreclaimed mining spoil, the iron and sulfur react with air and water and produce metal-rich acid mine drainage. The acid drainage collects in pits, seeps through unreclaimed spoil, and often contaminates off-site waters.
pH of the waters off this area was around 2.8 to 3.5. And the old spoils are cast out. Some, of course, slid over the hill, and back then they couldn't sell the top seam of coal, so they wasted it. So there was a lot of that strewn over the area and really making acid. So, it took a lot of years for it to break down to start healing itself somewhat. But for the most part, it was pretty desolate.
Unreclaimed coal refuse material, here seen in a flooded stream channel, can also generate acid mine drainage. Past operations, including unreclaimed spoil banks, are also unchecked sources of off-site sedimentation. The sediment can fill adjacent drainage ways and move downstream, causing flow disruption and flooding. Abandoned underground mines and auger holes act as conduits for acid mine drainage. As groundwater flows through them, it becomes exposed to pyritic material within the coal seam and the roof and floor material.
As the acid mine drainage seeps flow downstream, they hit the major streams that we're looking at here today, creating poor water quality. Also, we have a lot of failures as far as slips are concerned. So the loading along the bench causes slips that force the original ground down into the valleys, and that results in high sediment content within the streams, and they fill up with sediment.
These situations create a dangerous habitat for wildlife and pose a risk to water quality. More than 50,000 acres of such lands, requiring hundreds of millions of dollars to reclaim, exist in Ohio.
When it hits the air, it turns red like rust, and it coats the bottom of the stream. So when you look at this stream, the water itself may be clear, but the bottom of the stream is red, and it's full of flocculant where the iron precipitates out. That covers the substrate. It covers up the food sources for the bugs and the fish, and so they have no form, they can't eat, or there's no place for them to live. So
in 1972, Ohio passed a comprehensive surface mining law, and in 1977, the Surface Mining Control and Reclamation Act became effective on the federal level. It required states to pass laws meeting specific stringent mining and reclamation standards. Such standards include contemporaneous reclamation, regrading to approximate original contour, installation of drainage controls and sediment ponds to prevent off-site sedimentation, and water contamination during mining, saving of topsoil, resoiling, and revegetation. The Surface Mining Control and Reclamation Act also included provisions for reclaiming abandoned mine lands, but due to the high cost per acre to reclaim such sites, accomplishing the reclamation of all abandoned mine lands under the Act was found to be challenging. In addition, given the new reclamation standards in law, coal operators were concerned that they would be held liable for water quality and land reclamation on previously mined land left unreclaimed by others, and as a consequence, such sites were often avoided. Today, a program called Remining allows mining operators to return to these previously mined areas and mine and reclaim the land without being held accountable for the lack of reclamation by previous mining. This allows coal companies to obtain coal while freeing up abandoned mine land program funding for additional reclamation projects. Thus, remining allows previously mined land to be reclaimed without the specific expenditure of limited government funds. Remining has already demonstrated the ability to reclaim hundreds of unreclaimed acres per remining project. At remining sites, much of the coal under low cover of overburden has already been mined. Therefore, access to the remaining coal is more costly because a greater thickness of overburden must be removed to initially access any coal. This can be the single most cost-generating aspect of a remining site. A typical remining operation involves advancing existing high walls by taking 2 or 3 cuts into the contour of the hillside, each approximately 100 to 150 feet in width. In the case of area mining, the cuts advance completely through the hill. Both methods unlock the coal reserves behind the pre-existing abandoned high wall. Remining and reclamation result in improvements to water quality and land use, restoration of the hydrologic balance, and elimination of hazards to the public's health and safety.
So we're standing in Mccluney Creek. That's a tributary to the Mocklunant watershed. Comes in on the western side, enters into Mocklunant Creek at about river mile 18. About 2,000 acres of surface mines in here and about 900 acres of underground mines. So this area has been extensively mined. Ohio University's Winovich School has been involved with doing the asset mine drainage abatement and treatment plans, AMDAT plans. As a partner, we have a collaborative partnership with the Division of Mineral Resources Management. We've been working on watershed restoration and watershed characterization for the last 20 years. And so in the AMDAT, we proposed a phased approach, which was phase 1, we knew that Oxford Mining was in this area, and they were, back in 2005, thinking about remining as a potential for this area. And we've seen remining in other areas where the impact from abandoned mine lands in past coal mining is so pervasive that the remining can be an option to go in and restore and treat those abandoned sources. So those strip pits and high walls and leftover spoil can all be wrapped into the process of remining and reclamation at the same time.
Here at the Ohio State University Department of Civil, Environmental, and Geodetic Engineering, we have been conducting research and demonstration projects that are focused on innovative ways to reclaim abandoned mine lands for more than a decade.
There was 3 permits issued by the state of Ohio to Oxford. They all involved remining activity. The permits straddled both the Mocklunant and the Rush Creek watersheds. So that's the reason why we chose the 2 together. We found more evidence that remining does mitigate problems out there, including acid mine drainage, high wall spoils. Not only were 20 miles of high wall eliminated and over 470 some acres of strip mine spoil banks and pits eliminated, but there was also a noted improvement in the water quality, similar to what we saw in Duck Creek watershed. And what we saw the evidence was in the headwater streams, and that's where this mining took place, is in the headwaters of Mccluney Run particularly, and also in Rush Creek. And so that's a point where the pHs were around 3 to begin with before they started. And then we looked at their quarterly monitoring data as they moved through and reclaimed these areas and eliminated those sources. We found that the water quality actually improved 4 levels from in the severity index.
The secondary recovery of coal reserves through remining is important for 2 reasons. 1, economically, it recovers coal reserves that are often overlooked, financially difficult to mine, or essentially untouchable under general mining regulations. And 2, environmentally, it advances restoration of the hydrologic balance to watersheds beyond the remining site and provides a major uplift to the aquatic and terrestrial environment. General site conditions are improved, land use opportunities are elevated, and water quality within the downstream of the project site is improved. Studies have clearly documented the benefits of remining to aquatic and terrestrial environments.
So 2006 was when this site was initially mined. So they started mining on this ridge in this direction, and they moved around the watershed. So they start over here, and they actually progressively move around the watershed and end up on this side. This stream here, when I first started assessing it about 15 years ago, it was orange, it was full of sediment. There was at least a foot of sediment in here that filled the stream completely all the way up the channel, and had real low pHs. pHs were around 4, had high specific conductivity. There was no life here, it was a dead stream. So after BNN started their remining project, they built ponds. The minute they built the ponds, that increased water quality downstream because the ponds provided dilution. They also drained the pit ponds, which were the source of the AMD, and these streams started to improve. Over time, the sediment was washed out as a result of the storm water coming down through the streams naturally. And 15 years later, we have a beautiful stream that's got a lot of structure. It's got pools and riffles, it's got fish, it's got macroinvertebrates, it's got salamanders. We do assessments to determine the water quality out here. We do chemistry, which we take flow and samples of the water and send them to the lab. When we first started, this stream was full of fine-grained sand and silt and was completely covered with those types of materials, the very, very small materials. Those are not healthy habitats. And when it fills up with sediment, then there's not a lot of diversity. Either the pools are filled, the riffles are covered, so you just get kind of a very flat-looking stream that doesn't have a lot of characteristics to it or character to it. And so that makes it a poor quality stream for habitat. If you have a poor quality stream for habitat, then you're not going to have bugs coming back. So we can actually improve water quality, but if our habitat doesn't improve, that doesn't mean we're going to get a good quality stream in the end. We want to make sure that the habitat develops also. And that's why it takes a little bit longer for these downstream sites to improve, because it takes time for the physical aspect of the stream to develop as we move down from the mine site.
Regulatory agencies understand the important role remining plays in watershed restoration and are working cooperatively to provide remining incentives to the mining industry. The positive results of remining observed at the field level are compelling. Recognizing the value of remining as well as the additional operational and economic burdens associated with mining an unreclaimed site where the easily recoverable coal has been mined and where unstable high walls, spoil piles, and acid mine drainings exist, various incentives have been offered to coal mining companies, both at the federal and state levels, to encourage remining. For example, in 1987, Congress passed the Ray Hall Amendment to the Clean Water Act to assist in abating water pollution from unreclaimed areas. Mine operators in the past had been reluctant to remine areas with degraded mining-related water discharges due to the potential for long-term liability.
Mining companies could not get into these sites because there are pre-existing discharges out here that they would become immediately responsible for if they decided to come into a site like this. As soon as they turned a spade of earth, they were responsible for those discharges. Ray haul, what it does is it allows them to come back into these sites, access the coal, and as long as they don't make things worse and they do reclamation and do some pollution abatement, they can walk away when they're done. They take background or baseline water quality data, and based on that, they can get an alternate effluent limit based on what it looks like now before they go in and remine. And as long as they don't make it worse from that, based on that baseline, they're okay.
As a result of the Ray Hall Amendment, coal operators are encouraged to mine unreclaimed areas without being held liable for pre-existing water quality problems. Even though operators are not held liable for previous pollution, the result of remining is almost always a decrease in pollution, making this incentive extremely valuable. Through the remining process, the mine operator implements numerous best management practices, or BMPs, to conduct the remining project and reclaim both the abandoned mine areas and the coal reserves recovery area. BMPs tend to work in one of three ways: controlling the movement of surface or groundwater, improving the on-site geochemical conditions, or eliminating erosion and sedimentation.
Basically, what they are is a series of procedures either conducted during mining or during reclamation to improve the water quality. The most common one is just getting reclamation done out here. These old sites have been open for years. The water quality has been deteriorated for a long time and will continue to do so unless they get reclamation. Getting the site where you have positive drainage, you're getting rid of areas where the water tends to infiltrate in is a big part of it, and then getting something to grow on it, both of which will keep water out of the site by and large and reduce the acid load and the metals load. The reclamation, as I said, basically gives you positive drainage, so the water runs off rather than infiltrates into the mine spoil. When you get vegetation on there, it intercepts a lot of the water because it'll take it uptake through the roots, and the water never makes it into the spoil as well.
Well, the site consisted of a pit full of water, a number 5 coal pit. And the water had no outlet from the pit, so it accumulated there and gradually seeped through the spoil, causing excess loading of metals and high acidity load to the downstream waters. Secondly, the site, because of the acidic overburden and lack of topsoil, did not exhibit much vegetation. So that made the site susceptible to sheet erosion. So there was also downstream sedimentation loading from this site. So during the course of mining, we reclaimed the pit to current reclamation standards. That was probably the most significant BMP. In addition to that, the overburden analysis that was conducted prior to mining here as part of the permitting process identified an alkaline shale layer that we found to be highly erodible. Because of the lack of topsoil here, we used this weathered shale, stockpiled it, special handled it, and stockpiled it for use as an alternative soiling material when we were done. To ensure that acid mine drainage production would not occur post-mining, we also applied 10 tons to the acre of lime to the backfill before we put the topsoil down. That created an alkaline environment at the surface of the backfill so that any water that should percolate through the topsoil would be neutralized by that alkaline material to prevent any acid drainage reaction occurring post-mining. There was also a small underground deep mine here that had left a small gob pile, maybe of 100, 150 tons, that had been deposited directly in the headwater of one of the streams here. It was causing acid and metals loading to the stream. And we removed that completely from the site. We took it to an approved coal refuse disposal site. In addition to that, the establishment of vigorous growth of grasses and legumes here has stopped and prevented any sheet erosion from the site. Everything worked as planned here. The property has been reclaimed to current reclamation standards. There are 2 landowners involved here. Both landowners are productively using this land. This is an alfalfa field here. Across the way, they're cutting hay and grazing cattle. So we have eliminated the pollution sources here and returned the ground to productive use. Our industry, working in partnership with the state regulatory agencies, looked at this site and saw this as a potential for best management practices to result in environmental lift to the downstream waters. and we carried out the plan as proposed, and it worked as planned. Aesthetically, it's obviously a lot more pleasing to look at, a nice farm field as opposed to abandoned pits and spoils. It also eliminated a safety hazard.
There are numerous benefits that result from remining. First, reclamation of abandoned areas is gained without the use of abandoned mine land program funds. Second, in significant numbers of cases, water quality improves. Third, with the elimination of high walls and pits, the land is returned to a productive state. Fourth, aesthetically, the scars from past mining are eliminated, and the land now blends into the surrounding landscape. And fifth, physical hazards such as flooded mine pits, exposed high walls, and open underground mine entries are eliminated.
Well, from my experience, remining's been enormously successful. We've gotten thousands of acres reclaimed that the AML program would probably never get to, the abandoned mine land program would probably never get to. Number one, you're gaining reclamation of sites that have been open and unusable for years. Two, you have a strong possibility of improving the water quality. And three, the land gets back into a usable form. Reducing the amount of erosion and sedimentation will naturally happen on these sites because they've been open for years. Every time it rains, you get a big wash of silt and that sort of thing into the streams down here. Not only the best management practices, but also how much improvement we were seeing in water quality occurring from remining. And looking at how many acres we've seen remined at that time. The bit of research I did, I looked at 112 sites, which was over 250 discharges. And we saw an improvement in the acidity loads at about 50% of those sites. We saw an improvement in the iron and manganese loads in a large number of those sites as well. Less than 1% we saw a failure.
The Ohio Department of Natural Resources Division of Mineral Resources Management is very supportive of these efforts of our coal mining industry to conduct secondary recovery operations in a sound environmental manner that improves the water quality and landforms of impacted watersheds. We are working to create a regulatory framework that provides incentives and improves the permitting process for these sites. This is critical to Ohio operators and provides certainty within the permitting process. We want to provide a regulatory framework that will promote and not discourage remining.